Hi everybody, welcome back to Chem 161. What do we got going on this week? So, we're almost out of the quarter, like, there's 2 weeks left, and in fact, I'm going to run out of slides, so I might not even need to use all 4 lectures that are left, because we've just been going along at quite a clip, so, the short version, I guess, is that we are doing good. We're almost done with all the class content. What does that leave us to do? So there is going to be a quiz for Chapter 4 when we finish Chapter 4, which will probably be this week. We have lab worksheet number 4, that's due on Wednesday. Also, there are course evaluations that are opening up. Later tonight, I will go and hit a button, and then I will paste the link so that people can follow that. I think that you can access them right now if you know how to get to them, but I don't know how that works. Our course evaluation system is so convoluted and dumb. And we're changing it next quarter, so this is the last time we had to do this. But every time I have to look this up. So I will get all that information out and available tonight. Small amount of bonus extra credit points if I get enough course evaluations back from students. I can see how many students have responded, not who. But yeah. Okay, so when I left off last week on Thursday, I had gone over the 5-step plan to make a Lewis structure with you, and we drew CO2 using that 5-step plan. Oh, I had to go release quiz 3 scores. Yeah, remind me after class if I don't do that. I'm terrible about releasing quiz scores because I don't get a notification that an assignment has closed, and so it's just whenever I think to check. And I have 3 different classes all on different schedules, so it's a mess. Let's see here. So we're going to follow this 5-step plan which we talked about earlier. Counting all of our valence electrons to put it in a bank. Making the framework of your molecule with the central atom, the element that is listed first. And then we are going to use the remaining electrons to fill octets. Do the external atoms first, then do the central atom. And then finally, if you have run out of electrons before everything has an octet, make multiple bonds to the central atom. So we did CO2, and we showed that structure. So this is my slides doing it, but I drew that one out. What I want you to do for our warm-up here is I want you to do ammonia here. So I'm going to leave this screen on there. I want you to go through the 5-step process with ammonia. And when you're done, we'll put the structure on the board here. So I'll give you like 4 or 5 minutes to apply all the rules to ammonia. All right, one more minute to draw your Lewis structure, and we'll go over the answer. All right, let's go over the answer here. Well, first of all, this is what you should get. But let's do this stepwise just to see the 5-step plan in action here. So step number 1 is to count valence electrons. Ooh, that's a terrible color. Hold on. I was using pink for some reason for the earlier class, but it's a little too bright for this. All right, so step 1 is to count valence electrons. And so we can do that. I got a nitrogen. Nitrogen is worth 5. And each hydrogen is worth 1. And I have 3 of them, so I have 8 total electrons to work with. All right, for step 2, we're going to establish our framework. So I'm going to put the central atom in the middle, and I'm going to put the other atoms just, somewhere around them. It's fine. And then I'm going to connect them. And that cost me 6 electrons. So I have 2 electrons left. Step 3, I should do outer octets, but it's all hydrogen. Hydrogen, remember, hydrogen only can do this, right? And if I add one more electron, it will have a full n equals 1 subshell. Actually, that wouldn't even be a subshell. That'd be just a shell. So that's stable. So hydrogen just wants to have 1 additional electron shared with it in a bond. For our inner octets, I'm going to put the remaining 2 electrons on the central atom. And then for the last step, we'll do multiple bonds, except we don't actually need to. So there's our structure. Everything is great. Now, admittedly, that was probably the simplest structure I could give you. So I'm going to give you some more difficult structures on the next page, just so we can get more practice with it. All right, so here are some structures that I want you to draw the Lewis symbols for, or Lewis structure of. Now, there is an extra little thing that I have thrown in here to sort of, I don't know, monkey wrench up the works, throw a spanner in things, that sort of thing. And that is, well, what do you do if you have a polyatomic ion that has a charge on it? Well, when you're counting your electrons, for example, if I was counting my electrons here, I'd say carbon is 4, oxygen has 6, and there are 3 of them. And then I have to deal with this. Well, when I make something have a charge of -2, that's because I've added 2 extra electrons, right? So the total number of electrons in this structure would be 18 plus 4 plus 6 is 24. Likewise, for NH4+, to make something positively charged, you need to remove an electron. So you would deduct an electron from your total for NH4. And then you'd follow all the remaining steps as normal. So go ahead and draw the structures for SO3, CO3 2-, NH4+, PCl3, ClO2-, and NO+. To the best of your ability, you will have to make multiple bonds between atoms. None of these should break the octet rule yet. SO3, there is a temptation to do it. But don't worry about that just yet. And we'll go over the answers in just a moment. So like 5 or 6 minutes. 1 or 2 more minutes, and we'll go over the answers. All right, let's go over these answers here. So let me do something with our little template here so that we can reuse it. All right, so I can do that, and then now I should be able to draw whatever I want to. Woo! And then just boop. Okay, perfect. Always test that, right? All right, so for the first molecule we're going to look at for SO3 here, I don't actually write that over there. I can write it over here. So sulfur is 6. Each oxygen is 6, and there are 3 of them. So I have that many electrons to work with. Now I can do my framework. I'm going to put the sulfur in the middle. I'm going to just put the oxygens around that side. I'm going to space them out. Later on, we're going to talk about geometry, and so you'll see why I'm doing it this way. We'll connect them, and that's 6 electrons, so there we go. I'm now going to do the outer octet, so I'm going to go 1, 2, 3, 4, 5, 6. There's an octet. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That's all my electrons used, so we're down here. We've done all these things. Inner octets, well, I don't have any electrons left, so I can't do that. So I have to go to this step and make multiple bonds. So I'm going to pick any bond. I'm going to start with this one. And I'm going to remove 2 electrons from this atom, and I'm going to move them into the bond to make a double bond. And now everything has an octet, and so the structure is done. So this would be the Lewis structure I would expect for SO3 at this point. All right, so we got that. We can erase it now. And we'll do the next one. Now I got carbonate. And so we already did this before. So I should have that many electrons. So now I can do my framework. Carbon goes in the middle, and we'll just put the O's around the outside. Hey, this one might look a lot like SO3. And it turns out it totally is, because it's the same number of electrons, right? So connect, connect, connect. There's 18. So we did this, we did this. Now we could fill in our octets on the outside. There's 6, there's 12, here's 18. Oh, look, we're out of electrons. Oh, there's not enough electrons. Let's take any pair of electrons and make a double bond. Boop, there you go. Now, with ions, there is one last thing that you want to do, just to be clear that it's an ion, and that is you want to put square brackets around your structure, and then the charge goes in the top corner. So that is just shown somewhere to let people know, oh, this is an ion. If you don't put the brackets, then it's a little bit unclear. All right, we'll erase, and we'll do the same thing again for ammonium. Now, when I have a positive charge, I have to deduct an electron, because to make something positive, you remove its electrons. So this has 8 electrons. Now I'll do the framework. Nitrogen in the middle. I'm just going to put hydrogens all around the outside like this. And you're going to notice that when you go do, oh, I used all the electrons. And it's totally done. I just need to do this to it. So, very basic structure. Way easier than dealing with connect the dots, although this is probably the easiest structure of the bunch. All right, let's do PCl3. So phosphorus is 5, chlorine 7. There are 3 of them. I have 26 electrons around this one. I'll just arrange them like that or so. So let's connect 2, 4, 6. That leaves me with 20 electrons left. Let's do our outer octets. 2, 4, 6, 8, 10, 12, 14, 16, 18. Oh, interesting. I have leftover electrons. Those are going to go on our inner atom. Right here, 1, 2. And in this case, I do not need extra electrons from the outer atoms to contribute to bonds, because everything has an octet. So there's PCl3. All right. 2 more to do. So I have that many electrons for my chlorine and my oxygens. I'm going to add an extra electron from this minus. That gives me 20. I'm going to do my framework. Something like that. So 2, 4. And then I need to use my 16 electrons. So 2, 4, 6, 8, 10, 12. And then that would be my outer octet. So now my inner octets, I'll just go 1, 2, 3, 4. And it's done. Looks good to me. All right, and then the last one here, NO+. Here I only get 10 electrons. So N is the central atom, but there's only one atom attached to it, so you just do something like that. And then outer octets, so that's going to be oxygen over here. So there was 6 electrons, so I have 2 left. We'll do our inner octets by doing this, but I ran out of electrons. So that's as far as I got. So now I do need to do multiple bonds. Nitrogen only has 4 electrons, though, so I need to share a pair to get 6 and a pair to get 8. And so now everything has an octet. So NO would look like this. Or NO plus, I should say, would look like this. All right, any questions, let me know. We can now draw the Lewis structure for anything. We're going to draw more complex molecules later on, because what we're about to cover are situations where the octet rule isn't our guiding principle. In fact, one of these situations I've already delineated right here. If I go back to our 5-step plan, right here, the central atom in your structure may end up with more than an octet. We're going to talk about why this is in the next few seconds. All right. So let's talk about exceptions to the octet rule. The first exception is hydrogen, which we've already talked about. Hydrogen only has the n equals 1 shell. If you share 1 electron with it, it will have a full 1s2 orbital. N equals 1 is completely full. Hydrogen is happy. That's really all it can do. And our subtext for the hydrogen scenario here is we just call it the duet rule and say, oh, okay, hydrogen follows the duet rule. That's great. Hydrogen is doing its best. It can only take 1 more electron. So hydrogen does not follow the octet rule. Now, other situations will occur if you have an electron deficiency. And what that means is that the number of electrons that you have for your structure is odd. So we did NO plus, where we had 10 electrons. But regular old NO has 11 electrons. How do you satisfy the octet rule with an odd number of electrons? And the answer is always, you can't. It's impossible. How do you end up with an odd number of electrons? Well, if you add an odd number of things in there, so nitrogen only brings you 5, so that's going to make your total odd, right? Nitrogen's pretty guilty of this. Phosphorus can do it. There are many common ones that are sort of beyond the scope of this class. So, for example, the superoxide polyatomic ion, which is O2 with a 1 minus charge. The term for these you may have heard used is called free radicals. And so we hear all about this free radicals. Oh, they're bad for you. Eat antioxidants. They will protect you from free radicals. And what we can talk about here is that, very obviously, something that is a free radical is going to be very reactive. So this right here is going to immediately seek out an electron and go to fill its octet. The takeaway, though, is what do you do for the Lewis structure? Well, you follow all the rules that we've already done. Fill the octets of the outer atoms first. Fill the octet of the central atom last, and put any electrons that are left over there. If you don't get to the octet but you're out of electrons, so be it. Don't ever exceed the octet rule by making multiple bonds. Like, don't do that. But anyway, here are where those structures end up falling when we get the answer. The bottom one, NO2, has 2 structures. We're going to talk about resonance in a little bit. But they are equivalent. You can think of it as just rotating the molecule around. Although, in a bit, we're going to talk about that in more detail. Now, some elements, when they form ionic compounds, will try to just be n equals 1 full, and that's it. So, like lithium with a +1, or beryllium with a +2. When you start to get towards the non-metals, though, for example, boron, it behaves a little bit weird. Bf3 is a pretty common compound with boron, but you'll notice that it did not follow the octet rule. It could, but there's just not really enough electrons to go around. And if we try to make a multiple bond situation here, you're going to notice an issue real quick. And that issue is that fluorine would have to make a double bond, and fluorine doesn't want to give away electrons. We're going to approach that idea in a later section. We talk about formal charges. But it turns out that boron is very reactive and will react with something that has 2 electrons that can be given to it to form a bond. And so that looks kind of like this. If I take something like ammonia and I do this to it, then boron will say, hey, I'll form a bond with you. I'm not sharing any electrons, though. I don't have any. And nitrogen says, well, that's fine. I have 2. And you create this sort of structure, as shown on the right. It's called an amine borane. Amine boranes are quite reactive, and then, well, they react with each other quite well. And then the result is very interesting. In the laboratory that I worked in, the Goldberg lab, which no longer exists at UW because Karen Goldberg went to, I believe, University of Philadelphia. But we worked with amine boranes. Not me specifically. I did a different project, but there was an amine borane project in the lab to use as a hydrogen fuel because amine boranes form a solution as opposed to storing hydrogen in a gas form in a tank under your car, which could explode or rupture. And we were allowed to power a very small hydrogen car. Like, by small, I mean like a little model car. And it definitely worked. The problem was that getting hydrogen from amine boranes is slow. When I say amine boranes in that circumstance, instead of these fluorines, we had hydrogens here. So this is actual ongoing research, although I think the project has been pretty much scrapped at this point until a new catalyst is found. But the point here for this is that boron will only have 6 electrons, and it will ruin my pen. That's what it'll do. Boron will only have 6 electrons around it, and even though it is electron deficient, this is okay by itself, but the second it finds an opportunity for something to react with it and give its electrons, or take electrons from something, it will do that to complete an octet. So yeah, this is very unique to boron, but it is also very common for boron. And we'll see this a little bit more in third-year chemistry problems, which beyond the scope of this class, so we're just going to move on. Now, these have all been exceptions that are relatively uncommon. Let's talk about the most common exceptions to the octet rule. And those are what happens when I find a compound that has multiple atoms around its central atom, where the multiple is a number greater than 4. So for instance, like this is PCl5. I've omitted the electron pairs because there were just too many to draw out in my program. The term that we use for this is called hypervalent. Something is hypervalent if it breaks the octet rule. It's got more than 8 electrons around it. So this has 10 electrons. Now, if you've read the slide here, you'll notice that this happens for third row elements, but never for second row elements. Now, there's got to be a reason for that, right? And that reason is, well, when I am making bonds to stuff, so let's suppose that I have like nitrogen or something. Nitrogen has a 2s orbital and a 2p orbital. So there's what nitrogen looks like. And when I form 3 bonds to nitrogen to give it an octet, its orbitals would look like this. It'd be totally full. Where would I put any extra electrons if I wanted to make a 4th bond? So, like, I could have NH5 or something like that, or NH4 minus, or I don't know. If I wanted to have 5 elements around it, I would need to put those electrons somewhere, but there's no more 2p, or there's nothing in n equals 2. The next thing I'd have to put them in would be n equals 3, and that's too far away from the nucleus. So I can fit at most 8 electrons around nitrogen. This is the limit. But for phosphorus, I have d electrons and orbitals available. So for phosphorus looks like this. And so what I do when I put in all these electrons is if I'm going to have 10 electrons around it total, that's just going to look like this. Because the d orbitals are available for n equals 3 or higher, you can make more than 8 electrons around the central atom possible. In fact, the maximum for a 3d orbital, since this is 10 right here and this is 8, you can have up to 18 electrons around an n equals 3 atom. So what that means is you could potentially form up to 9 bonds around a central atom, provided that that atom, the central atom anyway, is in row n equals 3 or lower. Now, what you will find is that practically this doesn't happen because 9 atoms is too many atoms around a central atom to actually effectively fit. The other atoms will bonk into each other and there's no space. So, generally speaking, the most that we see is 5 or 6 because trying to cram a 7th one in there, it's just too tight. We can't fit it. There's room for the electrons, but all the electrons repel each other, and that's an issue. So this is where that 4th step comes into play for our 5-step plan to create the Lewis structure for anything. And that is, well, if you have extra electrons, shove them on the central atom. You can totally do that. However, the central atom must be n equals 3 or higher in order for you to exceed the octet rule. And that's because you have to have those d orbitals available for you to put the electrons in. All right. So now I've got more structures here. Oops, I didn't mean to do that. What I want you to do is I want you to draw the Lewis structures for all of these. But if you break the octet rule, that's fine. Note that the central atom is the only one that's allowed to break the octet rule. And for all of these structures, except for PO43-, you'll notice I have a little note here. It doesn't break the octet rule yet, but it will. And you'll see why in a little bit. So draw PO43- however you want to. There are multiple solutions at this point. There's one I'm expecting you to draw. We'll go over the answers in about 5 or 6 minutes, and then we'll take our break after that. 1 or 2 more minutes, and we'll go over the answers here. All right, let's go over the answers here. All right, we got the same little setup here. It's just that when we do these, step 4 is going to be very relevant for all of these molecules. Let me do this real quick here. There we go. All right, so for phosphate here, this one's not going to break the octet rule as we draw it. So phosphorus is 5. I got 4 oxygens, and I get these extra 3. So what is that? 24 and 8 is 32. And so that's going to look like this. 2, 4, 6, 8. 24. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. That's all of them. Everything has an octet, so everything's good. We'll just put our square brackets around it. And do that. There's our phosphate. Hooray. That one's pretty straightforward. Now, what we're going to find out later in the next section when we come back from the break here is that the correct Lewis structure, or the best Lewis structure anyway, is actually to do this. And you might think, well, what the hell? Why would I do that? Why would I make one double bond? And we'll talk about that in just a little bit. Let's go to the next structure here. So we got Xenon Difluoride. What? Xenon noble gas? It's going to participate in bonding? Yeah, it totally does. Xenon is actually big enough to do this. And fluorine is so electronegative that it's willing to take electrons from xenon. So, same sort of situation here. I'm just going to count valence electrons. 14 plus 8 is 22. We'll do something like that. 2, 4. So there's 4 electrons used. We're going to do outer electron octet, or outer octets. 2, 4, 6, 8, 10, 12. That's going to leave 6 electrons left. We're going to just put all 6 on xenon. So 2, 4, 6. And it breaks the octet rule, but xenon is in an element, or xenon is in a period that is 3 or higher. I believe it's in period 5, right? I should know that off the top of my head. Yep. So it can do this. And so there's our structure. All right, let's clear. We'll do IF4 minus. So got 7, 4 times 7, then 1. So 35 plus 1 is 36. So I'm just going to go I, F, 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 F. We'll just, not F minus, there we go. We'll just throw them somewhere. We don't know where they're going to go yet. So 2, 4, 6, 8 means I have that many electrons left. And then I would fill my outer octets, so 6, 12, 18, 24. Means I have 4 left. So I'm going to put the last 4 on iodine. There you go. It is an ion, so we'll go like this. And we're all set. All right, let's do IF5. So 35 plus 7 is 42 electrons. And by now, you probably get the point of how this works. So 1, 2, 2, 4, 6, 8, 10 electrons for bonding. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Where do the last 2 go? They go on the central atom. There you go. Notice how we're never really going to end up with multiple bonds for these, because I have extra electrons. They just get dropped on the central atom. It's fine. All right. I'm going to just give you the Lewis structures for the last few. So SCl6 looks like this. Dot, 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 dot. I have these more or less memorized because I've just done so many of them. So there's SCl6. And we'll do ASF6 minus, which is exactly the same. Dot, 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 dot. Just this one has an ion. Something you will notice as you do these structures is that if the electron counts are the same, you get the exact same structure. So for example, SCl6 here has 48 electrons. Down here, this one... Oh, I messed that up. Hold on. There are 6 of them, and each gives you 7 plus 1. 42, 47, 48 electrons. What do you know? And so they look exactly the same, don't they? I have something in the middle with 6 atoms coming off of it. And that's going to be true for these types of structures, is the electron count is going to basically dictate what you get. And that the identity of the atoms is not super important. So we'll discuss that a little bit more when we talk about geometry. So we'll do that after the break. So we're going to take a 10-minute break. Let's get some more Donkey Kong music coming up here, if I can find the right window. There it is. And I'll see you in just a little bit. Oops, I should probably unmute myself before I start talking. Welcome back. Let me wind this down here. So the next section, we're going to take our Lewis structures, and we're going to apply a sort of model to them. And that model is going to help us figure out what to do in a situation where we have equivalent structures, but like one just sort of intuitively feels better. And here's the example I throw on the screen for everybody. Why do we do this on the left as opposed to this on the right? There's really no good reason to say why we would do something on the right, right? Like, it technically works, but it's not symmetrical, and that bothers us, and that's gross. But that's not a very convincing reason, right? Like, they are equivalent. Or are they actually equivalent? So what we're going to do is we're going to introduce this concept that shows how they actually aren't equivalent. And that concept is called formal charges. So, looking at these atoms, I want you to try and think about where the electrons are relative to each of the atoms. And if you can deduce a way to rationalize why that seems odd, that's going to be a good foundation. So I'm going to give you like just a second to think about that. All right. Let's introduce the concept of formal charges. Here's how formal charges work. We're going to calculate the number of electrons around an atom relative to what it contributes to the molecule at whole. And so what that means is we're going to use this formula. So the formula for formal charge is equal to the number of electrons it started with minus the number of electrons currently available. Sorry, I'm sneezing here. I had to mute the mic here. The caveat that we're going to employ here, though, is that all bonds share electrons equally. In other words, I'm going to go like this, and I'm going to say, okay, how many electrons are available around this oxygen? Well, if each of these lines is my electron, I'm going to split the electrons evenly between atoms. So I'm not going to double count them. I'm only going to count what's available after I've shared away the electrons equally. So the way that this is going to work is we're going to calculate the formal charge for every atom. So I'm going to circle this atom right here. How many valence electrons does oxygen contribute to the molecule? Like, what does it bring when it starts? And so you should go, oh, well, there's 6 of them, right? Minus, how many electrons does it currently have as part of this molecule? So you'd go, okay, 1, 2, 3, 4. There's 2 bonds, but each bond we're going to count is equally shared, or just 1 electron per bond. So the formal charge of oxygen here would be 0. Let's go look at this oxygen over here, though. With a triple bond, I have 3 bonds, each of which I'm going to count an electron from, and 2 electrons in this non-bonding pair. So I started with 6, but I only currently have 5. So I have a formal charge of positive 1. Then let's look at this one over here. Again, start with 6, but how many do I have now? 1, 2, 3, 4, 5, 6. We're going to count the bond as 1. This oxygen has a formal charge of negative 1. So formal charges are a way of assigning charges to molecules, although these charges don't actually exist. They're just a representation of where are all the electrons in this molecule. Now, because this carbon is the same, or I'm sorry, not carbon, this oxygen is the same as the other one over here. They have the same formal charge. But what we would say is that, oh, okay, the oxygens on this molecule are equivalent. They're identical. There's no electrons shuffled between them. But on the molecule on the right here, we would say that all the electrons got moved over in this direction. And that doesn't particularly make sense, does it? Why would one oxygen have less electrons available to it than the other oxygen at the far end? So what we would conclude is that separating charges is unusual and strange. Why would oxygen separate out electrons? Neither of them can pull the electrons more strongly towards themselves than the other, so they should be equally distributed, right? They have the same electronegativity, you would expect it to be roughly equal. All right, so when we get our total formal charges, let me erase all of this. Where's my cursor? That's way up there. We get these numbers. And separating out charges doesn't really make sense for the same electronegativity. So, the closer your formal charges are to 0, the better your structure is. And so what we conclude is that this is the proper structure because it minimizes formal charges. So if you have multiple possible ways to rearrange double bonds or something, the best possible arrangement is the arrangement where the formal charges are minimized. You may not always be able to get them to 0. For instance, over here, in the thiocyanate ion, the formal charges will always equal the overall charge on the ion, and that's going to be -1. So no matter what I do, I have to have a formal charge total of -1. Otherwise, I've totally messed up the structure. So what I want you to do is calculate the formal charges for each of these elements. Remember that the formula is number of electrons it started with minus the number of electrons currently accessible or available or whatever. So calculate out all your formal charges for all the N's, C's, and S's here. And I want you to tell me which structure is better, left or right. Now, you'll notice here that you'll just have a -1 floating around. Which side do you think you should put it on, though? One more minute, we'll go over the answers. Sorry, I got distracted there. Somebody was asking me a question outside. All right, so let's calculate the formal charges here. So I got nitrogen. Nitrogen starts with 5 valence electrons, but here it's got 1, 2, 3, 4, 5, 6. 6. So there's its formal charge. I should be writing these with the charge second, actually. There we go. Carbon starts with 4. 1, 2, 3, 4. It currently has 4. And then sulfur. Oops, I don't need to draw a line around it. Sulfur starts with 6. And currently has 1, 2, 3, 4, 5, 6. So our -1 ends up on the nitrogen over here. Let's look at the other molecules. So here I got nitrogen starts with 5, ends with 1, 2, 3, 4, 5. Okay. Carbon is still 4 minus 4. And then sulfur starts with 6, ends with 7. So now my minus is on the sulfur side. Which is more appropriate? The answer that is suits the best structure is that this is the best structure. And the answer is, well, I have a -1 and I have to put it somewhere. I cannot get rid of it. So I'm going to stick the -1 on the side that's more electronegative. Nitrogen is more electronegative than sulfur. And therefore, we're going to choose that structure. So the double bond structure is better in this case than the triple bond single bond. Now you might think, oh, okay, well, what if I did something like this instead then? Would this be better? And the answer is, well, now the formal charges would look like this. So I'd have 5 minus 7, which is -2. This is still 0. And then this is +1. Should I make it more negative at the expense of making something positive? And the answer to that is, well, no, we still want to minimize formal charges. So this one's no good because we're just separating out charges unnecessarily. We want to minimize formal charges, but when you can't minimize them to 0, stick the charges where they logically make sense. So don't go to the extremes to try and follow the electronegativity rule. Use that as a guide when you have multiple competing options that are equivalent. All right. Now, again, just a reminder, formal charges are just a model. These don't actually exist. So they're not actually charges around nitrogen and sulfur here in these structures. The overall molecule has the charge. All right. So here are a bunch of structures that you've drawn already. So you can flip back to your notes to find NO+, SO3, O3. And what I want you to try and do is try and draw any additional alternative structures that you can. Now, you'll notice for NO, you can't, because you can't violate the octet rule, right? But for SO3, you can. O3, I just wanted to throw ozone on there because it's a segue to the next topic. So if you draw ozone and you're like, well, this is weird, there's a reason for that. Very important for ozone, do not do this. Ozone does not form a triangle, and we're actually going to talk about why that is later on today. Hopefully we'll get to that. But don't do that. Make sure your O's are in a line and it doesn't make an enclosed equilateral triangle. SO3, though, you should be able to draw multiple Lewis structures. In fact, you draw so many Lewis structures for that. And then go back and find your phosphate and draw out the correct structure that minimizes formal charges. So do all these exercises. 5 or 6 minutes or so. We'll go over the answers together. 1 or 2 more minutes, and we'll go over the answers. All right, let's go over the answers here. You're going to notice as we do these problems, I'm going to put the don't on here just because we're going to talk about that real quick, is that we're going to start to hit a point where we're going to have all these rules, and it's not going to help us terribly much. And we're going to have to rely on experimental observations, so... Oh, just a second. Sorry, I knew I had to cough, so I had to mute there. So, when we drew the Lewis structure earlier for NO, we got this. And this is the only Lewis structure that we can do, because I can't possibly put more than 8 electrons on nitrogen. So, this one's just sort of how it is. But for SO3, I believe we did something like this before. And we said, well, this satisfies the octet rule. But if we do formal charges, what we'd calculate for formal charges for oxygen here is this is 6 minus 7, which is -1. Same for over here. This one ends up being 0. And then for the sulfur right here, sulfur starts with 6, but it only has 4 available. So can I reduce these formal charges further? And the answer is, well, if I break the octet rule, sure I can. And it turns out that the best one for sulfur trioxide is actually this, where you just double bond everything, and now I just have zeros everywhere. Now, experimentally, how do we verify that this is the case? Well, if you measure the bond length of SO in this, and you find, oh, they're all the same, that's a good argument to say that they're all double bonds. Because double bonds should be shorter, right? There's more electrons between the nuclei, so they should all attract to each other that much more strongly. We're going to talk about bond length a little bit later. All right. We got ozone. Ozone's weird. in terms of its structure. And the reason for that is because here's the correct structure. So I connect these two. We do octets on the outside. So there was 8, 16 of my 18 total electrons. Here's 18, but then I get to this point, and it's like, well, what do I do? I don't have an octet on oxygen. I need at least that. So we got to make a double bond on one side. And then you might ask, well, why didn't I just do it on the other side? What does it matter? So we'll draw that one out too. And now we're going to do formal charges. So for formal charges, this is 0. This one's -1. And this one's +1. That's kind of gross, right? But when I get down here, all I did was flip them. Oh no. Is there a way for me to get 0? And you might have tried drawing that triangular one and gone, well, yeah, but this has zeros. Why isn't this okay? These are all fine. If I calculate the formal charges, it's all 6, start with 6, end with 6. Why can't I do this? And the answer is that this angle right here, between one bond and the other, these angles are too small. We're going to talk about that in a later chapter. Not a later chapter, sorry, a later section. Same thing. There's a specific geometry that molecules want to adapt to. And if you strain too far past that, the molecule just doesn't form. So O3 can't do this. We are stuck with one of these structures for O3. But which one is it? Do I double bond the left one or the right one? And the answer is, well, pick one. Doesn't matter. Now, in a second, we're going to talk about why it doesn't matter. But let's go to phosphate real quick here. So I'm going to run out of space, but... So I drew earlier that for phosphate, this was the best Lewis structure. Because it minimized formal charges. And so if you calculate the formal charges, phosphorus is going to be starts with 5, ends with 5. This oxygen is going to be starts with 6, ends with 6. But each of these oxygens is going to be starts with 6, ends with 7. And the whole thing has to equal -3, right? So really, I just have to have these floating negatives all over the place. Now, you could say, well, I could just I could do something like this and have the -1 be on the phosphorus. Because I'd have a 1- here, a 1- here, and a 1- here. But then we're putting the electronegative atom, or I'm sorry, we're putting the minus charge on the phosphorus, which is less electronegative than oxygen. So this is not as preferential. This is the best structure. If I make more double bonds, I'm just stacking negatives on phosphorus. And that's not something that we want either. So formal charges help us minimize the number of structures we have to choose from and can narrow it down to, oh, this is the best structure. But sometimes even that doesn't help us, and that's an issue that we're going to get into right here. So what's the deal here? Why do I have equivalent structures? And it turns out sometimes that happens. These structures aren't identical because if I were to label them in some way, so if I called this one A, B, and C, for example, maybe I had a different isotope of oxygen. So OA was actually like oxygen 16, but OC was oxygen 17. Then they'd be different, right? They look the same, and they have all the same formal charges, but spatially, if we label them, they're not the same. And so what we're going to do is first we're going to call these a special sort of circumstance. These are called resonance structures. Whenever you have an arbitrary choice between structures, what we do is we say two things. One is that they are resonance structures of each other. And then the second thing, which is really creepy, the actual structure is the average of all the resonance structures. And we draw a little double-headed arrow between resonance structures to indicate that they are resonance structures. So in other words, if we were trying to figure out what the actual bond length was, we would not say that ozone has a single bond and a double bond. Instead, what we would do is we would take the average. How do you average bonds? The way that you do that is the following. So we'll go back over here. Oh, we don't need that anymore. All right, so there's our structures. What I'm going to do is I'm going to look at a position in our molecule. Let me get a different color here. So I'm going to look at this position right here. And we're going to calculate the average bond length. Or sorry, bond strength, we'll say, because we're counting numbers of bonds. And so what we do is we calculate like this. So we go number of bonds divided by number of resonance structures. So in the left position that I've circled, I have circled 2 bonds on the left plus 1 bond on the right. And I've done this over a total of 2 structures. And so this would be equivalent of me saying that each bond in that position is the equivalent of a 1.5 bond, or 3/2 bond. So a 3/2 bond would be it'd be stronger than a single bond, but it would be not as strong as a double bond. And then if I circled the other position, I'd get the same thing. And so what I would conclude is that the bonds in ozone, and specifically actual ozone, they're both 1.5 bonds and they're equal strength. So they are identical to each other. Now that's weird, but it does sort of make sense, right? I have all O's, they're all identical. So I should have the electrons distributed between them evenly and not have these floating formal charges that just sort of mirror wherever they should go back and forth. And the issue that we're really hitting here is our models are breaking down. The models that we're designing here, so our Lewis structure model, our formal charge model, our resonance structure model that we've come up with, like these are all great models most of the time. And then occasionally we're going to get a molecule, and here's our molecule, it's ozone, where everything gets ruined. Nothing really quite models ozone correctly. And this is just sort of a consequence of models. The models can't perfectly model everything. So when you get to a situation with resonance structures, it's important to note that resonance structures are just our patchwork for our model. The formal charges are going to be distributed across the molecule our resonance structures are going to make it basically so that they're all equivalent. But in reality, what we actually see for ozone is the average of all the resonance structures, whatever that average ends up being. So we're going to do another example of that with nitrate, I believe, in a second here. When you draw resonance structures out, you indicate that structures are resonance structures of each other with this double-headed arrow here. So make sure you include that. So for the last example we're going to do today, I want you to draw the Lewis structures of nitrate. So draw NO3-. You're going to notice that you can move the double bond wherever you want to, so you're going to have that many structures. And then we're going to calculate the bonding in NO3. It's not going to be a single bond. It's not going to be a double bond. It's going to be some average between them based on how many structures you draw. So I'm going to give you, I'll give you 5 minutes or 4 or 5 minutes because we're almost out of time. And then I'll draw the structures, and then we'll be done for the day. So see you in a bit. All right, we're out of time already, so let's go over the answer here real quick. So let's describe the bonding in NO3. First, we got to draw its structure. And oops, we don't need this anymore. So really quickly, you should be able to draw the Lewis structure for nitrate. And you should get something that looks like this. But you could have put the double bond in a different position, say over here. Or you could have put it in the other position, over there. These are all equivalent, because if I count the formal charges here, I'm going to get +1 for nitrogen here. These are each -1. And here's 0. And I can't do anything about minimizing these, because I can't make an extra bond. I would break the octet rule. I don't have extra orbitals available for n equals 2. So nitrogen this is just the best you can do for nitrogen. All you can do is shuffle this double bond around so that the formal charges move about. What we're going to do is we're going to calculate the bond strength. We're going to pick the top position here. So I'm going to just circle the top position for all of them. So I've circled a total of 2 + 1 + 1, or 4 bonds, over 3 structures. And so in that position, I would find that the NO bond is the equivalent of a 4/3 bond, or 1 1/3. And so we could determine that, okay, that means it's slightly stronger than a single bond, because 4/3 is bigger than 1. But it's less than a double bond. And that makes sense, because if it was as strong as a double bond, there'd be a double bond in every position here, right? So that's our average bond length. So we can use resonance structures to determine the types of bonding and how they rate versus single versus double, and so on. I think the next question asks you to look at NO2. There's our structure. Well, oh, okay, it's SO3 and SO2. Or S32-. Okay. So I'm going to leave these problems for you to try. Oops. Because we're out of time here. So try drawing SO3 and then SO32-. You're going to notice that for some of them, there's resonance structures, and some of them there's not. We haven't really talked about bond length yet. We will do this probably later, but stronger bonds are shorter, and then longer bonds are weaker. Oops, we'll do it this way. So if you're doing these problems and trying to answer these questions, that will help you do that. Right now, we're just primarily focused on which bonds are stronger. So like a single bond is not as strong as a double bond. And then whatever fraction you get is wherever you are in the middle there. So that's resonance. I'm going to leave these exercises for you. When we come back on Thursday, we're going to do geometry and polarity. We'll probably do intermolecular forces, and then we'll be done with Chapter 4, which means we have all next week to do Chapter 5. And Chapter 5 doesn't take more than like a day and a half, so we are doing pretty good. All right, that's all I got. Thank you to everybody for coming out to the lecture. Again, make sure that you get that lab worksheet in on Wednesday. I'm going to go open up all the course evaluation stuff after class today to have that all available. And then let me know if you have any questions about anything or whatever in the Discord. All right. Yeah, that's all I got. See you on Thursday.